In this video, we're going to look at the divides relation on the integers, and we will look at some elementary proofs involving the divides relation and some guidelines for doing proofs. Just a recap of Module 1, we talked about various sets of numbers, the natural numbers, capital boldface N, the integers, capital boldface Z, capital boldface Q is the rational numbers. These are the fractions with numerator and denominator integers, and then the real numbers, the numbers represented by points on a line. And in this video, which sort of begins the course, we're going to specialize and talk about the integers. Divisors and multiples in the integers are something you're probably familiar with. So as you know, 20 is a multiple of the integer 4, because 20 is 4 times 5. And when we say that one integer is a multiple of another integer, we mean that the first integer is an integer multiple of the second integer. In other words, here's the definition of the phrase A is a multiple of D. Assuming A and D are integers, A is a multiple of D means there's some integer k such that A is D times k. And k is sometimes known as the multiple. So when you want to demonstrate that one integer A is a multiple of another integer D, ordinarily you have to find the k that works. So 51 is a multiple of 17, for example, because 51 is 17 times 3. The k that works in this case is 3. Usually we use the terminology of divisors rather than the terminology of multiples when we are talking about this concept. So rather than saying A is a multiple of D, usually we will say D is a divisor of A. So for example, 4 is a divisor of 20 because 20 is a multiple of 4. The definition is identical to the definition of the phrase A is a multiple of D. D is a divisor of A means there's some integer k such that A is D times k. And as before, to demonstrate that D is a divisor of A, you find the k that works. So for example, 17 is a divisor of 51 because 51 is 17 times 3. K equals 3 is what works in this example. Try another example. Is 471 a divisor of 411,183? Well, according to the definition, we would need to determine if there is an integer k for which 411,183 is 471 times k. And the way to do this is to divide both sides of the equation by 471. In other words, we're solving for k. If the k turns out to be an integer, then 471 is a divisor of the number on the left-hand side. If k is not an integer, then 471 is not a divisor. So doing the calculations, k would be 411,183 divided by 471, which I did on my calculator and got 873. Which is an integer, so 471 is a divisor of 411,183. And in general, the way to check whether or not D is a divisor of A is the easiest way is almost always to divide A by D and see if the answer is an integer. The only exception is the case where D equals 0. For example, if you want to check whether or not 0 is a divisor of 522, you can't divide 522 by 0. If you try it on your calculator, you'll get an error message. So we have to go back to the official definition to check the divisor relationship when D is 0. In other words, we have to check whether or not the number A is D times some integer k. So is there an integer k such that 522 is 0 times k? Well, the answer is no. No matter what number k is replaced by, 0 times k is going to be 0, not 522. 0 is a divisor of 0, but as this previous example shows, for any non-zero integer a, 0 will not be a divisor of a. A little bit of terminology and mathematical notation here. The phrase D is a divisor of A is sometimes shortened to D divides A, and the shorthand notation for the phrase D is a divisor of A is this D vertical slash A. So this is read D is a divisor of A or D divides A. So a few examples here. 6 divides 42. Because 42 is 6 times 7. Minus 6 divides 42. Because 42 is a multiple of minus 6, namely minus 7 times minus 6. 6 divides minus 42, because minus 42 is 6 times minus 7. And last example on this slide, minus 6 divides minus 42, because minus 42 is a multiple of minus 6, namely 7 times minus 6. So one thing this example shows us is that when you are checking the divisor relationship between two integers, the signs of the integers don't really matter. So here are some properties of the divides relation that sort of correspond to the previous example. If A and D are integers and D divides A, then minus D divides A. If D divides A, then D divides minus A. If D divides A, then minus D divides minus A. So here's sort of a general statement, a precise statement of the fact that when you're checking the divisor relationship, the signs, plus or minus, of the numbers involved don't matter. So let's look at a proof of item 1. Item 1 on the previous slide was that for all integers A and D, if D divides A, then D divides minus A. A few preliminaries before we get to the proof. Here are some basic steps to get a proof started. First, write down what you know, your assumptions. Usually you'll begin those with the word assume. Write down what you have to show using the assumptions. It's always good to precede these by a phrase like, we have to show. Then rewrite what you have to show using definitions. Ideally, this will result in an equation or possibly an inequality that you have to show. And then do any obvious simplifying in that equation or inequality. Fourth step, begin the argument by using definitions to rewrite your assumptions. So we began in step 1 by writing down the assumptions. Here in step 4, we rewrite them using definitions, and ideally you'll be able to write your assumptions as equations or inequalities. And you might begin the rewriting with the phrase by our assumptions. And then finally, step 5, to finish up the proof, you have to derive the equation in item 3, the thing you have to show, from the equations in item 4. So hopefully this procedure will take a proof and reduce it to deriving an equation from other equations. So now let's look at the proof. We are proving for all integers a and d. If d divides a, then d divides minus a. Step 1, assume a and d are integers and that d divides a. We have written down our assumptions. We have to prove that d divides minus a. Based on the assumptions that we have made. In other words, using the definition of divides, this means we have to show that minus a is some multiple of d, that minus a is d times k1 for some integer k1. By our assumptions, or assumption in this case, we know that a is d1 times k2 for some integer k2. We've used d divides a and the definition of divides. And now we somehow have to derive this equation, minus a is d times k1 for some k1, from this equation, a is d1 times k2 for some integer k2. Okay, so it follows that from this equation, a is d times k1, that minus a is minus d times k2. Sorry, the assumption, this follows from the assumption a equals d times k2. Minus a is minus d times k2. Doing a little bit of rewriting, that means d is that means minus a is d times the quantity minus k2. So d is k1, where k1 is the integer minus k2. We know that the negative of an integer is always an integer, and so k1, defined by the equation k1 equals minus k2, will be an integer. And we are done. Here's an alternate way to finish the proof that we just did. So up to this point, where we have rewritten our assumptions, this proof and the proof on the previous slide are going to be identical. So by our assumptions, we know that A is D times K2. And now we have to argue that minus A is D times K1 for some integer K1. In this version, we're going to start by saying what K1 is. The K1 that works is going to be the negative of K2. Let K1 equal minus K2. Then K1 is an integer, so to complete the proof, all we have to show is that minus A is D times K2.